The journey of every car tire begins in sprawling manufacturing complexes, where natural rubber from Southeast Asian plantations arrives in compressed bales weighing over 200 pounds each. Natural rubber is harvested as latex from rubber trees, then processed into solid bales for shipping. Each bale
Insistence. Synthetic rubbers complement natural rubber in modern tires. Styrene butadiene rubber provides wear resistance.
Carbon black, produced from petroleum, provides the reinforcement that makes tires durable. This finely divided carbon gives tough heating.
Carbon black particles are incredibly fine, with surface areas exceeding 100 square meters per gram. This enormous fluffus. Silica increasingly replaces some carbon black in modern tires, particularly for wet grip performance.
Dozens of chemical additives contribute to tire performance. Sulfur enables vulcanization. Accelerators control cure rate. Sulfur is the essential ingredient for vulcanization, the chemical process that transforms soft rubber into the durable, elastic material cord.
Textile cords provide the structural reinforcement within tire bodies. Polyester, nylon, and rayon fabrics. High-tensile steel wire forms the belts that stabilize tire treads. These precisely drawn wires, stronger than steel bead wire, forms the critical connection between tire and wheel. These wire bundles, wound into precise rings.
The Banbury Mixer Hall houses the enormous machines that blend rubber compounds. These
Banbury mixers use powerful rotors turning within enclosed chambers to blend rubber compounds. Hydraulic rams apply tremendous.
Every ingredient is weighed with precision before mixing. Compound formulations specify exact percentages.
Automated systems load precisely measured ingredients into the mixer in specific sequences. The order of addition affects.
During mixing, rotors spinning at different speeds shear and blend the materials. Temperatures rise above 250 degrees.
Temperature monitoring is critical during mixing. Too much heat can begin premature vulcanization, ruining. Completed compounds drop from the mixer onto mill rolls below. This hot, pliable rubber mass will be further processed.
Two-roll mills continue processing the compound, squeezing it between heated mill-lated rollers.
The compound takes on its final characteristics during milling. The smooth, uniform appearance indicates proper dispersion.
Milled compound is cut into continuous strips for cooling and storage. These strips will be fed into subsequent processes that form specific tire components.
Cooling conveyors reduce compound temperature before storage. Proper cooling prevents premature vulcanization. Properly compounded and cooled rubber displays uniform color and texture. Quality testing verifies each batch
Laboratory testing verifies compound properties meet specifications. Tensile strength, elongation, hardness.
Different compounds are stored separately, each formulated for specific tire components. Tread compounds differ from sidewall compounds.
Every compound batch is tracked from mixing through the finished tire. This traceability enables quality management and support.
High-performance tires require specially formulated, optimized for grip, heat resistance. Compound quality teams review production data continuously, identifying trends and implementing improvements. With compounds prepared, manufacturing moves to component production, where rubber transforms into the specific elements that will be assembled into complete tires.
The component manufacturing hall produces the dozen or more elements that combine to form a tire. Each component is
Tread extrusion forces compound through precisely shaped dies, creating the continuous strip that becomes the tire's coffin.
Modern tread extrusion uses multiple compounds simultaneously. The tread surface may use one compound for grip, while the
multi-compound treads visible before vulcanization show distinct layers that will have different functions. Extruded tread cools on conveyors before cutting to precise lengths. Each cut piece contains exactly the material needed. Cut tread segments show the compound characteristics that will determine tire performance. Surface appearance and dimensional accuracy are verified before release to tire building. Sidewall extrusion creates the flexible panels that connect tread to bead. These components must flex millions of
Inner liner calendaring produces the thin rubber layer that replaces traditional inner tubes in modern tubeless tires. The inner liner's smooth, uniform surface is essential for air retention. Even tiny defects could cause slow leaks. Textile calendaring applies thin rubber coatings to reinforcing fabric. These rubberized tendons, massive calendar rolls, some exceeding 6 feet in diameter, apply precise rubber thickness to textile substrates.
The textile pattern remains visible beneath the rubber coating. These precisely aligned cords will provide directional strength. Body ply cutting produces fabric pieces at precise angles, typically 45 to 90 degrees to the direction of travel. Steel belt calendaring embeds high-tensile wire into rubber sheets. These belts, positioned under the tread, stabilize.
Steel wires in belts are aligned at precise angles, typically 20 to 25 degrees from circumferential.
Belt cutting produces strips of exact dimensions for tire assembly. The steel content requires specialized cutting equipment.
Bead winding machines wrap high-tensile steel wire into precise bundles that will anchor tires to wheels.
Completed beads represent the interface between tire and wheel. These precisely wound wire bundles will grip the rim with forces exceeding 4,000.
Bead filler extrusion creates the triangular rubber wedge that supports the sidewall to bead transition. This component affects ride comfort and handling response.
Bead assembly combines wire bundles with rubber filler into completed units ready for tire building. This sub-assembly Schaefer strips provide abrasion protection in the bead area where tire contacts wheel rim. This protective component prevents damage from rim edges during mounting and driving. Component staging organizes all elements needed for tire building: tread, sidewalls, plies, belt.
Automated guided vehicles transport components, maintaining continuous supply.
Component inspection before tire building verifies dimensions, weight, and appearance meet specifications. Component weights are verified to ensure correct material quantities. Weight variations could indicate improper dimensions or compound issues requiring investigation. Robotics. Visual inspection identifies surface defects, contamination, or dimensional issues. Trained agents. Ahead lies tire building, where individual components combine into complete tire assemblies. The precision
A modern tire contains over a dozen distinct components, each precisely manufactured and quality verified.
Tire building machines await components for assembly. These sophisticated systems will combine rubber,
First stage tire building begins the assembly process that transforms individual components into complete tire structures.
Tire building begins with the inner liner, applied to the drum as the first layer. This airtight membrane will eventually...
Automated systems apply inner liner with precise positioning. The seam where material ends meet must align perfectly to maintain airtight integrity in the finished tire.
Body plies wrap over the inner liner, their textile cords providing the structural strength to contain inflation pressure. Most
Stitching rollers press body plies to remove trapped air and ensure adhesion between layers. Air pockets could cause separation.
beads are positioned at exact locations that will become the tire's interface with the wheel rim. Precise placement ensures proper bead seating and air seal in the finished tire.
Turn-up mechanisms fold body ply edges around the beads, locking the bead into the tire structure. This critical step creates the mechanical connection that anchors the tire to the wheel. The turned-up ply wrapping the bead creates tremendous holding force. This elegant engineering solution has secured
Sidewall components are applied to the first stage assembly. These flexible rubber panels will protect the carcass plies while providing the tire's visible exterior surface.
collisions. The completed first stage assembly forms a flat cylindrical band, not yet recognizable as a tire.
The first stage assembly transfers to second stage building, where it will be shaped and combined with belts and tread.
Inflation pressure begins transforming the carcass from flat cylinder to the familiar donut shape. The body plies stretch and re-enters. The belt package, pre-assembled from steel-reinforced rubber strips, positions over the expanding carcass. Presingle. The interface between carcasses and belts must achieve intimate contact with no air entrapment. Proper bonding here to
Tread application adds the final major component, positioning the rubber that will contact the road. The tread wraps around the belt package, completing the tire's exterior. Tread stitching presses the rubber firmly against underlying components, removing air and ensuring adhesion. Stitching rollers work methodically across the entire tread surface. The pattern and pressure of stitching affects air removal and component adhesion.
Shoulder stitching addresses the critical transition between tread and sidewall. This area experiences complex stress. The completed green tire, so-called because it's uncured, takes shape on the building machine. Though it
The green tire's smooth tread shows no pattern, appearing nothing like the finished product. The familiar tread design will be molded during
Green tires require careful handling as the uncured rubber can be deformed. Any distortion at this stage could cause uniformity problems in the finished tire.
Tire inspection verifies assembly quality before the irreversible vulcanization process.
Innovations. Inspectors verify bead positioning, ply splices, belt alignment, and overall dimensions.
Barcode application enables tracking through curing and subsequent processes. The barcode links to building machine. Green tire storage holds inventory awaiting curing. Storage time is limited as the uncured rubber can degrade. Green tires load onto conveyors feeding the curing area. The transformation from soft, shapeless assembly to finished tire will occur in massive heated presses. The green tire's soft texture demonstrates its uncured state. After vulcanization, this same rubber will become firm. Ahead lies the curing area, where the magic of vulcanization occurs. Massive presses.
Tire curing presses apply up to 350 tons of force while heating tires to over 300 degrees Fahrenheit.
The tread pattern originates in the curing mold, carved as a negative image into the press segments.
This mold creates green tire loading, positions the uncured assembly in the mold. The tire must center precisely for uniform curing and proper tread pattern formation.
An inflatable bladder inside the press will expand during curing, pressing the tire against the mold. This in turn.
The press closes with tremendous force, beginning the curing cycle. Inside, the green tire will transfer.
Rows of curing presses operate continuously, each completing a cycle every 10-15 minutes. The curing hall is where rubber undergoes its permanent transformation. Vulcanization, the chemical reaction that
Operators monitor critical curing parameters continuously. Temperature, pressure, and time must remain within intervals.
Curing temperatures typically reach 300 to 350 degrees Fahrenheit, high enough to drive the vulcanization reaction, but not so high as steam systems supply the heat for vulcanization. High-pressure steam flowing through press platens maintains the precise temperatures needed throughout the curing cycle. Bladder systems inflate inside the tire during curing, pressing the rubber against the mold. Pressures can exceed 300 psi.
During curing, the inflated bladder presses the tire outward while the mold compress inward. This pressure, combined with heat,
Curing time is precisely controlled, typically 10 to 15 minutes for passenger tires. Longer cycles is ensured. The press opens after the curing cycle completes, releasing steam and revealing the transformed tire.
The newly cured tire displays its molded tread pattern for the first time. The smooth green tire has transformed into a... Extraction systems remove the hot, cured tire from the press. Surface temperatures can exceed 200 degrees Fahrenheit.
Post-cure inflation maintains tire shape while the rubber cools and sets. Without this controlled cooling, the
post-cure inflators simulate the wheel rim, supporting the bead while internal pressure maintains the tire's shape. Cooling may take 10 to 20 minutes depending on tire size. The freshly molded tread pattern shows crisp detail, from major grooves that channel water to fine sipes that provide additional.
Sidewall molding creates the raised lettering and markings that identify the tire. Brand name, size designation, speed range.
The DOT code molded into every tire indicates manufacturing plant and production date. This marking enables
fully cooled tires release from post-cure inflation for transport to inspection. The vulcanization process is complete for limb. Cured rubber demonstrates the elasticity that distinguishes vulcanized material from uncured rubber. This property,
mold maintenance between cycles, removes any rubber residue and ensures clean pattern transfer. Proper mold care directly affects tire appearance and quality. The inspection hall subjects every tire to comprehensive quality verification, visual inspection, uniformity testing.
Its aids. Visual inspection identifies surface defects, including blisters, cracks, or contamination. Trained inspectors.
Automated vision systems complement human inspection, scanning tire surfaces at high speed. Pattern recognition software identifies.
Uniformity testing measures how the tire varies around its circumference. Variations in force or geometry could be. A loaded wheel presses against the rotating tire, measuring force variation. Even small variations in radial
Uniformity results show force variation around the tire circumference. Specifications set maximum allowable variation. Grinding stations can correct minor uniformity issues by removing small amounts of rubber. This precision correction brings
Precision grinding removes high spots that cause force variation. The amount removed is minimal but sufficient to bring uniformity within acceptable limits.
Balance testing identifies weight imbalances that could cause vibration, while wheel weights can correct imbalance during mounting.
X-ray inspection reveals internal structure invisible to surface examination. Belt position.
Sidewall inspection verifies appearance quality, including lettering clarity and surface finish. Cosmetic standards ensure tires meet brand image requirements. Bead dimension verification ensures tires will fit wheel rims properly. Incorrect bead dimensions could prevent mounting or cause air leaks during service. Tires failing inspection are marked and diverted for investigation or scrap. Rejection data feeds back to manufacturing for continuous improvement. Defect analysis investigates rejected tires to identify root causes. Understanding failure modes enables process improvements that prevent future defects.
Cutting rejected tires reveals internal defects for investigation. This destructive analysis provides insights impossible to obtain from intact tires.
Statistical process control tracks quality metrics continuously. Trend analysis identifies emerging issues before they become significant problems. Quality teams review inspection results regularly, analyzing data for improvement opportunities. This commitment to continuous improvement drives industry-leading quality levels.
Tires passing all inspections receive approval markings enabling shipment. This final quality gate ensures every tire reaching customers meets exacting standards.
Approved tires proceed to packaging and shipping. The journey from raw materials to finished product is complete, with quality verified at every step.
Laboratory testing supplements production inspection with extended verification. Destructive tests verify internal.
Load testing verifies tires can support weights well beyond their rated capacity. These safety margins ensure reliability even under extreme conditions. Lotions. The finishing area prepares approved tires for delivery to customers worldwide. Final processing, labeling, and cleaning removes any processing residue from tire surfaces. This final cleaning ensures tires arrive to customers in pristine condition. Labels apply retail and technical information to each tire. Fuel efficiency ratings, wet grip grades, and noise levels help consumers make informed purchasing decisions. Palletizing stacks tires efficiently for shipping. Configuration maximizes truck capacity while protecting tires from damage during transport. Shipping labels route each pallet to its destination. Sophisticated logistics systems track every tire from factory to customer worldwide.
Warehouse storage holds inventory for global distribution. Modern tire factories serve customers across continents. Container loading prepares tires for ocean shipping to international markets. Global tire companies serve customers worldwide.
Loaded trucks depart for destinations worldwide. The sophisticated engineering and manufacturing within this in retail showrooms, these tires await vehicles and drivers. The engineering excellence of modern tire manufacturing.
At installation, the tire begins its service life. The thousands of engineering decisions and manufacturing steps now support real-world driving. On roads everywhere, these tires perform their essential function. Grip, durability, comfort, and efficiency all. The tread pattern molded during curing now channels water and provides grip. Engineering decisions made months ago affect every moment of driving. Inside a modern tire factory, chemistry, engineering, and precision manufacturing combine to create the essential.